Nowadays, many small food and beverage businesses need good daily planning to make sure their ingredients are used properly and profit can be maximized. If production is not well planned, it may cause wastage, shortage of ingredients, or low daily income. Therefore, a systematic method is needed to help businesses owners decide how many products should be produced each day. This project focuses on a beverage kiosk located at Harun Aminur Rashid College Cafe, University Pendidikan Sultan Idris, UPSI, also known as the FOC kiosk. The kiosk sells several types of drinks such as green tea, chocolate, and iced tea. Each drink is prepared in a 500 milliliter cup and sold at a fixed price of 3 ringgit. However, each type of drinks uses different amounts of powder, sweetened condensed milk, and water. At the same time, the kiosk must follow daily ingredient requirements such as minimum usage of powder and maximum limits for milk and water. Because of these limitations, the kiosk needs to determine the best number of servings for each drink that can be produced every day. The main problem is to find the optimal combination of green tea, chocolate, and iced tea that satisfies all ingredient constraints while maximizing daily revenue. In this project, linear programming is used as a mathematical method to model the situation and help the kiosk make better production decisions.
Now, I will explain the model formulation for our linear programming problem. Our objective is to maximize the daily revenue of the kiosk by deciding the number of green tea, chocolate, and iced tea servings produced each day. First, we define our decision variables. Let x1 be the number of 500 ml servings of green tea, x2 be the number of 500 ml servings of chocolate, and x3 be the number of 500 ml servings of iced tea produced each day. These variables represent the quantities that we want to determine. Next is our objective function. Each drink is sold at a fixed price of 3 ringgit per serving. Therefore, the total daily revenue is given by 3 times x1 plus 3 times x2 plus 3 times x3. So our objective is to maximize z equals to 3x1 plus 3x2 plus 3x3. For the constraints, the total powder used from green tea, chocolate, and iced tea must be at least 900 grams per day. The total sweetened condensed milk must not exceed 2,350 ml, and the total water use must not exceed 46,600 ml per day. Finally, all decision variables must be non-negative, which means x1, x2, and x3 must be greater than or equal to 0, because we cannot produce a negative number of drinks. In conclusion, we combine the objective function and all constraints to form our linear programming model. This model will help us determine the optimal number of green tea, chocolate, and iced tea servings to maximize the daily revenue while satisfying all ingredient constraints.
Now, I will explain how our linear programming model is set up in the Lindu software. Now, first, for the solver setup, this problem is formulated as a maximization problem. Therefore, the keyword max is used in Lindu. The objective function entered is z equal to 3x1 plus 3x2 plus 3x3, where x1, x2, and x3 represent the daily serving of green tea, chocolate, and iced tea respectively. Next, all the constraints related to ingredient usage are entered under the subject to section. These constraints include a minimum usage requirement for powder as well as maximum usage limit for sweetened condensed milk and water. The end comment is used to complete the model, and all decision variables are assumed to be non-negative by default. After running the solver, the output shows the message LP optimum found at step 3, indicating that an optimal solution has been reached. The maximum value of the objective function obtained is 300.9711, which represents the maximum daily revenue that the kiosk can achieve. The optimal values of the decision variables are x1 equals to 48.64, x2 equals to 23.32, and S3 equals to 28.37. Finally, for the interpretation, this result means that to maximize daily revenue, the kiosk should produce approximately 49 servings of green tea, 23 servings of chocolate, and 28 servings of iced tea. Already these costs are zero, indicating that each beverage contributes to the optimal solution. In addition, all constraints are binding, which shows that the available ingredients are fully utilized without exceeding their limits. In conclusion, Lindo effectively determines the optimal production plan that maximizes revenue while satisfying our operational constraints.
This presentation is about a sensitivity analysis. Sensitivity analysis is used to study how the changes in a model affect to the optimal solution. The purpose of this analysis is to discuss the effects of the changes in the two main areas, which are the right-hand side of the constraints and the objective function coefficients. First, we consider the changes in the right-hand side of constraints. The right-hand side represents the available resources or limitation in the model. In this case, all conditions remain feasible even when the right-hand side value changes. This means the optimal solution is still valid as long as the changes stay within the feasible range. Next, we examine the changes in the objective function coefficients. These coefficients determine how the decision variable contributes to the objective value. In these situations, all the conditions remain feasible even though the objective function coefficient changes. This shows that the model remains stable within a certain range. Using the Lindo result, the feasibility range for the objective function coefficient is obtained. Changes within this range will not affect the optimal solutions. In conclusion, sensitivity analysis helps us understand how the robust to the model. It ensures that the optimal solutions remain reliable even when small changes occur.
This maths programming project shows clearly how linear programming works in real life, mainly for business and factories. LP helps companies make the best choices to maximize profit while handling limited things like raw material, cost, and time. We study based on the operation of a beverage kiosk to show how maths help plan daily work, matching what industry and STEM jobs need, like managing operation, factory engineering, and data checking. Also, the LP Solver apps help us to solve math models step by step and identify the best answer fast. With sensitivity analysis, we saw how changes in limits of parts like raw materials or supplies affect the top profits. This shows why being flexible and making good choices is a key in real situations. Plus, this project helped us enhance our skill a lot. We learned teamwork, communication skills, and problem solving, especially when making maths model with problem statement, objective function, and constraint. In the end, it taught us math isn't just a book stuff, it's a strong tool for choices based on data in real life. That's all from us. Thank you.